Okay, hello everyone. Welcome back to the stream. This is, what number? Stream 6 or something, 6 or 7. And we're bringing on a return guest, who I will introduce in a bit. But first, before we bring on our guest, our special guest today, let me know if you can hear me and let me know where you're from. Where are you watching from? We usually have a very international audience. I know it can be hard for some of you to join at this time of the day, just due to time zone differences. So if you're up late or if you're up really early, thanks for joining. And even if you're not, thanks for joining as well. Okay, nice. We got a lot of countries. Kosovo, Egypt, India, Buenos Aires, Los Angeles, France. Awesome. Miami, where the weather is sunny and the people are shady. I'll keep that in mind. Chicago, Kashmir, Texas, Mozambique. Wow, very international. All the continents. So today we are going to be learning about MPLS, which stands for Multi-Protocol Label Switching. If you're studying for the Ccna, you don't really have to know a lot about MPLS. You just basically have to know what it is, what it does. It's basically a WAN technology, wide area network technology. But if you're thinking about going beyond the Ccna, you definitely should learn about MPLS, both for the enterprise track, the CCNP Enterprise, CCIE Enterprise. You do have to know MPLS, but even beyond that, especially in the service provider track, if you want to go CCNP service provider or CCIE service provider, you definitely do have to know MPLS. So basically for anyone, I think the stream will be very valuable. To be honest, I'm not an expert at all in MPLS. I've studied a little bit. I know what it does. I know the basics about the technology, but our guest today, Kelvin, knows a whole lot more about it than I do. So I'll definitely be learning a lot today also, along with you guys, I think. So if you remember Kelvin from last time, we did a stream a few months ago. He taught us about Juniper Networks, Junos, their operating system. And Juniper is another networking vendor just like Cisco. Today we're going back to Cisco, so he'll be showing us about MPLS on Cisco iOS. So let's get right into it. I will bring Kelvin on. Give me a second. Hey, Kelvin, you're on.
Hi there.
Hey, hi there. So it's been a couple months since our last stream. How have you been?
It has. You had to deal with Donald for your last stream. I'm so sorry about that.
Thank you. No, that was a good stream. Learned some Aruba. And I think since our last stream, you got your CCNP service provider. Is that right?
I did. I finally got off my butt and got it.
Awesome. So you've got two CCNPs now, right? Enterprise and service
Enterprise
provider?
Service Provider.
Yeah.
And
So-
for what it's worth, I've also got double J and CIP. So that's
Right.
for
So-
what it's worth, which is basically nothing. Okay.
Yeah, so he's got the Juniper equivalent of the CCNP, Enterprise and Service Provider, same tracks. So MPLS is a pretty big topic, especially on the service provider track, right?
Yeah, they love their MPLS on the service provider track. You have basically every exam on the service provider track touches on MPLS in some way, shape, or form, some more than others. So it's a decently big topic that you should be familiar with if you are trying to get into the service provider world, for a very good reason. Service providers just eat up MPLS.
Yeah, it's something you have to know. How about for the enterprise track, which I think most people, they go for enterprise first before service provider. What about the enterprise track?
That ends up being our recommendation there, is if you don't have a very good reason to stray from that path, to go for the enterprise track first.
Yeah.
For the enterprise track, it's a little bit more nuanced. So as I'll show you in a second, the Nrc exam has a little coverage of it as far as the theory. So honestly, if you're a CCNP enterprise candidate, you're trying to go for your Encore plus your Nrc combo, and then in particular regard to the Nrc exam, which is the exam that actually covers MPLS, if you understand the first, the theory part of it, which is going to be first 15-ish minutes there, you're honestly fine. Even if you don't understand the implementation, as long as you understand the components of MPLS, you're probably going to be just fine for the Nrc exam. Now, for the CCIE candidates, I don't know how many there might be in this audience, but for the IE candidates, the bar is set much higher. So you're going to be expected to know how to implement MPLS. You're going to be expected to understand from a service provider perspective even how you might implement MPLS there for elder VPN purposes.
Yeah.
And the reason that becomes important for the IE is because there are some enterprises. It's a niche implementation for sure, relatively speaking, but there are some enterprises that implement their own elder VPN for whatever design or business use case reasons. There are some businesses that will implement their own layered VPN services, and for that purpose, you're gonna want to have your CCIE candidates, the ones that are in the upper echelon of training, understand at least how to implement it if they are called to at some point.
Yeah, right. Okay. And I just got another question. How about CCNA candidates? I answered that very briefly at the beginning. You basically have to know what MPLS is and just know it's a WAN service and not much more
I
beyond
looked
that.
in the CCNA OCG before the stream started because I wanted to see how deep Odom covered it, because I haven't taken any CCNA. I don't know the depth to which they even tested on MPLS.
Yeah.
And as far as I can tell, Odom went a little deep on it. Mainly, as far as I can tell, on the objectives, you really just need to know how MPLS might be applied as a general WAN application, rather than what Odom goes into, which is the actual redistribution and stuff. I think he goes a little bit deep into the design. Not that that's a bad thing necessarily, just that I don't know that it's strictly necessary. Again, haven't taken it, so I'm not the authority on what's on the CCNA, but for the CCNA, the consensus seems to be as long as you know what applications MPLS could have and a general design understanding of it, you're probably fine.
Yeah, cool. All right.
Yep.
Shall we get into it? You good to go?
Sure.
All right.
Sure.
So
I'm going to go ahead and I'm going to switch between screens here because I have my whiteboard, my chalkboard on one monitor and everything else on another.
Okay, sure.
But here we go.
All right. I got you.
That screen
Full
share
screen.
working?
Yep, looks good.
All right. So just to get us started here, what I'm going to do is take a look at what the certifications cover. So I'm not going to look at the service provider track. I figure if you are going for your service provider CCNP, you can probably look into that yourself. I'm going to go ahead and look at what the enterprise track expects, and with the exception of some topics maybe in the end, the main focus of the stream is going to be on MPLS in the context of the enterprise.
Yeah, that sounds good.
Yeah. So if we look at the Nrc exam, so this is one of the concentration exams that you need if you're getting your CCNP. As a reminder, for the CCNP Enterprise, it's Encore, which is your core exam, plus one of a couple of specializations. I forget the exact count, but you're probably going for your Nrc unless you have a good reason not to. And as far as the VPN technologies go, this is the domain that we're focused on if we're talking about MPLS. You've got 2.1 and 2.2 that are going to be talking about MPLS. 2.3 is the MVPN, which we're not really concerned with in this stream. For the purposes of the Nrc exam, you need to know what a label switch router is, what the label distribution protocol is, the basic idea of what label switching is, and what a label switch path is. That's what these acronyms mean here. And you need to understand what a layered VPN is. So it's not too in-depth. You need to understand the design of an elder VPN, and it helps, in my opinion, for the Nrc exam, even if it's not strictly necessary for you to have implemented MPLS in the lab. But it's not strictly necessary on the exam in that you're probably not going to be asked, how do you configure LDP? It's just helpful to see the components come together, in my opinion, because elder VPN can be a fairly in-depth topic, and it might be hard to understand just from reading or from watching a video that covers good theory. Now, that's that for the enterprise, or for the Nrc exam. For the CCIE exam, you have an entire section here in the transport technologies, that this domain 3 here that covers MPLS, and here you're going to be expected to do implementation and troubleshooting. So you're going to be expected to understand how to implement LDP, how to implement, or how to understand how the label stack goes together. This can get condensed into a single term called OAM, which I'll cover in a bit. So MPLS ping and MPLS traceroute, they expect you to understand what OAM means. You need to know how to implement LGVPN, so how to route between the provider and the customer. That's what 3.1b1, that's a mess of an objective, is you need to understand what VPN v4, in terms of the AFI there, how it's implemented in BGP, and you need to understand what Xnet means. I'm not going to cover that one too much in particular in this stream. Basically, the idea is you leak in routes from other customers or partners or whatever the case may be, and you're essentially kind of breaking down the wall that MPLS builds between the customers. I'll cover that one more later, but as it specifically relates to route leaking, there are some resources online you can look into if you want to learn about it. Probably not going to cover it too much in this particular stream here, but it's fairly simple, so you should be able to get the hang of it within 5 minutes or whatever the case may be. So that's that as far as the objectives go. Now this is the topology you're going to be working with. There's a lot of routers, and the reason for that is that this is a fairly involved lab. There's a lot of things going on here, and we're not going to be working with this entire lab all at once. That would be a little bit chaotic there. So what we're going to do is we're going to go ahead and break this down. So the way that you best learn MPLS is first by reading up on it, so learning the theory behind it, and then as you implement it, you break down each component. So you implement the core first, you focus on signaling the labels, and then you focus on the customers. If you're labbing other VPN, that tends to be the best way to do it, so you don't get too overwhelmed by everything that goes into it. So before we do that, I should probably switch screens here. So stop sharing, and I'm going to go ahead and switch into, let me move this over here. I'm going to switch to my second display here, because I'm going to do a little bit of a chalkboard demo.
Oh, nice.
So let's start off with a simpler topology. So we're going to go ahead and just make a serial line of routers there. So we're going to have a source that's just sending traffic to you guessed it, destination. And we have a line of routers in between. So we're going to make this R1, R2, R3, and R4. That should be fine. So we're going to line these up here, like so. And we're going to make this prefix, let's say 10.0.10/24. So this guy is, let's say that this guy is dot 1. We're going to make this segment here 10.0.20/24, and then we'll make this guy dot 1 as well. So we have 10.0.1.1 sourcing traffic that's being destined to 10.0.2.1. Now, the way that you could set this up, you could do a number of ways, but the important thing is that every one of these routers here needs to be aware of both routes if you want bidirectional reachability, which is what ping is. Ping sends an echo request to the destination replies with an echo reply. And that involves every one of these routers knowing these customer routes here. And so you could do a number of ways. You could do a static route on each router, 2 static routes in particular. You could do things like Ospf or EIGRP or run a routing protocol there, where you advertise these interfaces here, the networks associated with them, into your routing protocol, into your IGP there. And from there, you can go ahead and get bidirectional reachability, because every single router in the middle, by virtue of having Ospf enabled on them, is going to learn those routes. The problem is that that may work for a small environment where you have a couple of routes there, but if you add more networks, if I add in their destination, if I add in their source, each of these routers has to learn those routes for the new networks. And that's problematic because as those networks grow, you gain more and more routes, and now every network you add, in total you're learning 4 new routes, because every router has to learn an instance of that route, which is a problem. So what you can do is, if you think about this topology, right? If we go ahead and send traffic from the source, it's going to hit R1. Now, R1 needs to know what the destination is. That's fair to say, right? Because it needs to know that I can push it on to R2, push on to R3, push on to R4. right? It's fair to say that R1 here needs to know about this destination. But does R2? R2, fundamentally, all it's doing is it's sending into R3. It doesn't really care what the network is. It just knows that the next hop is R3. Now, in this case, it needs to know what that network is because it needs to know that the next hop is R3. But if there's another way that it can be told that the next hop is R3, then fundamentally it doesn't have to care about the destination network. This can be, 69, 69, 690. This can be 192, 168, whatever. It doesn't really care what the network is. It just needs to be told, hey, this traffic needs to go to R4, which is the edge here. It's the one that's going out to destination. Just push in this direction, you'll be fine. That's fundamentally what R2's job is. Same thing for R3. So these two routers in the middle, they don't really have to know what our networks are. They just have to know where R1 is and where R4 is in the topology, because those are edge routers. Those are the routers that are actually connected to the source and destination. Hope that makes sense there. And so we can go ahead and cut down on some of this routing redundancy by implementing another system that we can use for R1 to tell R2, hey, you need to send this traffic to R3. Same thing for R2 to R3, R3 to R4, and down the line. This is where MPLS starts to come in. So with MPLS, what you can do is use a label. So if we think about our IP packet, right? So if I can draw a square properly, or a rectangle as it were. I am artistically challenged. Don't make fun of me. Good
enough. That's why we're in tech.
So we have our whatever here. Parts I'm really concerned about are the source and the destination. And then we have our, so this is the IP header. And then this is our Ethernet frame. I don't really care what's in here. It's just there. And then here is our MPLS header. So this is commonly called a shim header. It's because you're shimming it right in between the Ethernet and the IP header. And the idea is that list, alongside some other information, contains your label. And your label is some number. Let's say this is 16, which is the default starting range for labels on iOS XE there for MPLS. Now, if you are R1, right, this is the PE router. We don't really have a CE in this case, but we can say that these guys are the PE routers. Let's say you're running MPLS in this core here. When you hit the PE router, the PE router gets an IP packet, because this source and this destination are going to be completely unaware of the fact that there's any MPLS going on at all. So the source sends a regular Ethernet frame that contains a regular IP header, no MPLS yet. So after R1 de-encapsulates the Ethernet header, throws it away, and has just an IP header left, it's going to look up at the network and its routing table. It's going to do normal routing. And the routing table is going to tell it, okay, so you're about to forward it out to R2, but you need to put a label on it. You need to put an MPLS label on it. And this MPLS label is not going to tell it what the customer network is. It's not going to tell it what the actual destination network is. This label signifies that it needs to go to R4. And because it's within the service provider, R2 will know where R4 is because you're running OSPF within the service provider. So now you have this label, you can affix it on in front of the IP header, you do an encapsulation, and then you put on your regular Ethernet header, doing your frame rewrite as you normally would with just normal routing. Then you send this on, and R2 just looks like a label. It doesn't even look at the IP destination. So that means that you don't have to route these customer networks within the service provider anymore. The service provider routers here can be completely impervious of the actual customer networks. This is just looking at the label. And this 16 label is going to signify that you need to push it onto R3. There's a swap action that potentially goes on here, and we'll talk more about that later. And then when it gets to R3, it's going to go to R4. It's going to do the same MPLS lookup. It's not going to care about the IP destination, and it's going to move on to R4 and then to the destination. The destination gets a regular IP packet, no MPLS, because again, the source and the destination are completely unaware of the fact that MPLS is even happening. So that's a basic explanation of the use case for MPLS. If it seems confusing, it's probably because it is. It's hard to grasp in an abstract sense, but hopefully when you see it in the implementation, it's going to become a little bit more clear as to what we're actually doing.
Yeah. We got a few questions now, but I think I'll leave them for later. I'll just let you do your thing and see if you cover them.
Yeah. Okay. So that being said, let's go ahead and I'm going to stop sharing again. We'll move back to the chalkboard eventually, but I'm going to go ahead and move to my primary monitor because this is where our terminal is. So I was in a rush for time there, so I didn't actually get to IP address the routers properly. So that's what we're going to do.
Nice.
I put loopback addresses here. And what we're going to do is, first of all, I'm going to drag this off. That way I have an idea of what the interface names are that I'm configuring, because I don't want the same thing to happen as the Juniper stream where I mixed up the interfaces. And you remember that?
Yep.
So I have this pulled up here. So what I'm going to do first is go ahead and set up the core. So the core is going to consist of R1, R2, R3, all the way down to R6 here, including R16 and R17. So R7 to R15 are our customer routers. We have 3 customers, 3 routers per customer. That makes 9 routers for our customers there. And then everything else is going to be a service router core router. So we're going to set up the service router core first to support MPLS, and then we're going to build everything on top of it. Because the idea is you're building layers on top of it. So you need to have your service router, the actual transport, set up to run MPLS. And then as soon as you have that set up to run MPLS, as soon as you have that set up to transport the MPLS labeled packets there, everything is just building on top. So no matter what you run on MPLS, whether it's your layer 3 VPN, layer 2 VPN, or whatever else you're running on MPLS, your core is the same. So you set up the same no matter what, which is nice because then you don't have to reconfigure the core every time you want to run a new application. You just run a new application on top of it. So that's that. So what we're going to do is we're going to go ahead and configure our interfaces here. And I'm going to leave gig 1 unconfigured, and you'll see why in a moment. I'm going to go ahead and configure the IP address here. And while we're here, I'm going to set up OSPF 10.1.16.1. I'm going to make the OSPF cost here 100. That should be that. And from here, I'm going to run OSPF and IP OSPF 1 area 0, int 3 IP OSPF 1 area 0. So we go ahead and run a show IP OSPF interface command. You can see we have these 2 interfaces that are active in OSPF. We're just doing single area OSPF here. No real need to do multi-area, though you can engineer multi-area if you want to work with MPLS. It's just significantly a bigger pain in the butt. So that's that. And I'm just going to get R2 working so that we can go ahead and initialize our MPLS. And then from there, we can go ahead and speed run through the rest of the IP addressing.
Nice.
So IP address 10.1.2.2. And then router OSPF 1. Right. So in a moment, we should see that our OSPF neighbors form. So we're in the init state right now. Okay, that was quick. Probably because we don't have many routes to exchange. So there's multiple ways you can signal labels, and by signaling, I mean provisioning. So when you configure the actual core to learn labels for the routers, that's called signaling. And there's multiple ways you can signal labels, 4 primary ways. We're going to cover one of them today, maybe 2. So the first way you can do it is through IGP plus LDP. and Ldp is the label distribution protocol, and I'm covering that primarily because the objectives want you to learn Ldp. That's the simplest way to signal MPLS is using Ldp on top of your IGP, which is going to be Ospf in this demo. The second way you can do it is through Bgp. So Bgp has capabilities to transport MPLS labels, and that's part of what we're going to be using in the ElderVPN part of the demonstration. But you can also use it as a replacement for Ldp in a sense. You can use it to signal the underlying labels as well. That's the second way. The third way is through something called RSCP-TE. And RSCP, you might have heard of it if you've learned QoS. That's the Integrated Services QoS protocol. But there are extensions on top of RSCP that allow it to work with MPLS, and that's the primary use case you're going to see for RSCP today. RSCP failed in a lot of ways because it's very state-heavy. It requires the network to maintain a lot of state. But as far as MPLS goes, that's perfectly fine because you're just running RSCP internally within the service router to do the MPLS signaling. And RSCP, it's more complicated to design and implement, but it has a lot of advantages, primarily in the fact that it allows you to run QoS and traffic engineering over MPLS. That's the third way. The fourth way is actually really new. It's called segment routing, and Juniper, in its special sense, likes to call it Spring. So you might also hear it called Spring, source packet routing. But basically everyone else in their right mind calls it segment routing. And segment routing basically uses the IGP itself. So Ldp runs on top of the IGP in a sense. Not really, it's really an independent protocol, but it ties itself to the IGP in some ways. But it's an independent protocol, right? It's not within the IGP, it just utilizes the IGP learned routes in order to do label signaling, and we'll talk about that later. Spring, or segment routing, specifically uses the IGP to do the label transport. And it does this in a couple of ways. So there's 3 protocols that support Spring. Ospf, or I keep calling Spring, segment routing, Ospf, ISIS, and Bgp. So those are the 3 routing protocols that have extensions to support segment routing. And Ospf does it using the type 10 LSA. So you probably haven't heard of that being used too often, but MPLS actually has 2 use cases for the type 10 LSA. In the RSCP-TE use case that I mentioned as the third way you can signal labels, and as the segment routing use case that can also be used to do label signaling without the addition of Ldp. So that's the bleeding edge way. It has a lot of advantages, but we're going to do it the classic way with Ldp. So I have R1 and R2 set up here. They're IGP neighbors. Can't talk today. And I haven't advertised the loopbacks. Well, that makes sense. That's why they wouldn't be there. Okay. So we're going to advertise the loopbacks here, and this should change. Yep. So we have a routing entry here. So we're exchanging routes using Ospf. Now, there's 2 ways you can enable Ldp. I typically call them the dumb way and the smart way. The classic way to do it, the way you're supposed to do it, I suppose, is this command here under the interface. So it's one command to enable MPLS IP under the interface. And if you do show MPLS interface, you can see that we have the interface enabled here. The other way you can do it, and I much prefer this way 99% of the time, is based on the fact that you're going to have IGP enabled. So you're going to have IGP enabled within the ISP. You're going to need to have Ospf enabled. You might as well have a one-to-one relationship. And what I mean by that is you have interfaces that are enabled under Ospf. Most times, those are the exact same interfaces that you're going to want to enable under MPLS. So you could go through the effort of going under your interfaces, and for each interface, doing both IP Ospf 1 area 0 and MPLS IP. If you want to do it the smart way, there's a single command, MPLS Ldp autoconfig, and what this does is it says, look at the interfaces that are enabled under Ospf. So in my case, it's Gig 2 and Gig 3, and enable those interfaces under MPLS.
Oh, that's very
so
convenient.
for every interface that's enabled under the IGP, enable those for LDP as well, because chances are those are the exact same interfaces that are going to be running for LDP. Yeah. And so it makes it very convenient. It means that if you have new interface that you're adding into the service while you're scaling out, it means that you only have to remember to enable one thing, which is OSPF in that interface. And once you enable OSPF, LDP will automatically kick into action. If you want to override this behavior, let's say there's one particular interface that you don't want enabled for MPLS, you should just be able to do an MPLS LDP IGP autoconfig. And this will exempt it from the autoconfig. So if we do a show MPLS interface, you can see that's disappeared now from the output. So LDP is not enabled on it. Nice. So we can go ahead and re-enable this because I do want it running on that interface.
I think people who studied OSPF for the Ccna might recognize the passive interface default. It's sort of a similar mechanic. Yeah,
it's a similar idea where you passive interface every single interface, and then you can go back in, and if you have a particular interface you want to exempt from that rule, no passive interface. Yeah, it's the same idea there. I also want to go ahead and configure gig1 here. I mixed up the routers. 10.1.4.1. Gonna go ahead and enable OSPF, and you can see here, just to prove my point, LDP is enabled here. Now, before we go on and enable the MPLS functionality on R2 as well, I want to go ahead and take a look at two parameters. So MPLS, LDP, and there's a bunch of configuration you can do here. Most of it is beyond the scope of what I'm trying to cover here. Two of them are not. So the first one is Router ID. Now, if you think about something like OSPF, if you think about something like BGP, your routing protocols, those guys use router IDs to identify the routers. Some routing protocols have a bigger use case here than others. OSPF infamously will hate you if you use duplicate router IDs, but it's not necessarily significant reachability-wise. So if I want to go into OSPF here, I can make my router ID 0001. That's obviously not a valid IP address. I can't actually set that on an interface, but it'll work for my router ID. But for LDP, you can't do that because LDP's router ID isn't just for cosmetic purposes. It doesn't just exist to identify the routers. It uses it to identify the routers. It uses it to identify the LSR. It's called the LSR ID. But it's also used as a transport address. And what I mean by that will become a little more clear when I show you the packet capture for the LDP neighbor establishing itself. But the summary of it is that your LDP router ID has to be reachable. So let's say I make this LDP router ID my loopback interface. And by the way, what goes after here is an interface. It just grabs the IP address off of it. So let's say I go ahead and use my loopback for this. If the loopback is not advertised into OSPF, if it's not advertised into IGP, if my LDP neighbor doesn't know how to reach it, it's going to fail. So you need to be able to ping the router ID. That's a big deviation from your routing protocols that, as long as the router ID is unique, they don't really give a hoot what it is. LDP deviates from that notion. I can actually demonstrate that. I'm just going to go ahead and disable OSPF on the loopback. And that should break reachability. So even if I configure it on R2, it shouldn't work. The other parameter I'm going to show here is MPLS label range. And this is useful in a troubleshooting scenario. So you're not going to... LDP's labels are locally significant. It doesn't matter if multiple routers have the same label that mean different things. It's locally significant. It's just going to... it concern itself with what the labels mean to the local router. But changing the label range, and you can see what it is by default, show MPLS label range. It's by default, the lower bound is 16 and upper bound is 1,048,575. And that's a lot of labels. And you can keep it that way, and MPLS will work just fine. But in a lab, you're likely not going to need that many labels. It just the way it works is for every route that's going to make a label for, it counts up, it increments that in that label range, and it's just going to assign a label to every single route. You probably don't need that many labels, so you can repurpose the labels to mean something useful, which is troubleshooting. So you can see what particular router generated the label, and if you're a lab, you're trying to troubleshoot what's going on if your routers, if your MPLS is broken. A lot of times it can be really difficult to troubleshoot, and seeing where reachability breaks and then seeing what was the last label that you see in your output can be really helpful if you have a way to identify, based on the label, what router is actually causing the issue. So for lab purposes and for just ease of troubleshooting, you can go ahead and set a label range specifically. So for my labs, I tend to use 4-digit numbers there, where, so in this case, I have 999 labels to work with, which should be fine. So this is the lower bound, this is the upper bound. And if I set this, every single label that this router will ever generate will be between 1,000 and 1,099. If I go to router 2 and set the label range from 2,000 to 2,099, router 3, 3,000, 3,099, you get the point as the routers go on. That means that whenever I see any label that starts with 1, I can automatically assume this is the label that R1 generated. And I can go from there if I need to do troubleshooting. It makes it a lot easier to hunt down routers. So that's that. I will go ahead and say, if you go ahead and do a show MPLS forwarding table, you can see that we still have a label here, a local label of 16. And you can see the error here, 1 label's already out of range. That's a warning because iOS XE will not regenerate the label for you. So if you already have labels that were generated using an old range and you go ahead and switch to a new range, they're not going to regenerate the labels for you. So you have to reboot the router if you want to reset the labels. So if I wanted to make it so 2222 was within the 1000 range, I'd have to reboot this router, which I have no interest in doing in this stream. That's that. So now if I go ahead and go back on this router, I can go ahead and repeat the configuration steps, which is basically one command at this point. Mpls Ldp autoconfig. And mpls label range 2000, 2099. And mpls Ldp router ID loopback 0. So those are the 2 configuration commands there that we're going to use to configure MPLS. There's the mpls Ldp autoconfig. And you can see that we have MPLS enabled on this gig 1 interface, which is heading towards R1. And if we do a show MPLS Ldp neighbor, which is how you verify your neighborships, we see nothing because the router ID over here, 1111, if we go ahead and try to ping it, we'll see that we can't because I pulled it out of the IGP process. So that's just proof that you need to have your loopback advertised into IGP in order for LDP to form. So if we do a show MPLS Ldp neighbor now, we can see a lot of information. This is the summary command. There's a detail command that you can use, and that shows you even more. It shows you the capabilities at advertising, but a lot of the information you're going to need is focused up here. So we have our TCP connection, so this is showing what ports were used, what the addresses were, and you can see here what I mean, that the router IDs that were used, which are our loopback 0 interfaces, which are 1111 on router 1 and 2222 on router 2, are used as the source and destination address of our TCP connection. And then you can even see here which router was the receiving router and which router was the source router, as far as like TCP three-way handshake goes, based on the port numbers. And here's the other useful thing here, Ldp Discovery Sources. This tells you how Ldp discovered the neighbor. Now, this is important because there's a couple ways you can do discovery. So the main way that you're going to see if you're using Ldp is dynamic discovery. And if I can pull out my annotation here, the dynamic discovery works like this. So let's say we have these 2 routers here. If I can draw a less pitiful circle, We have a link here. So we have IGP running here, and we're running LDP. Now the way this works is we're going to be using UDP multicast, and I'll show you more in the packet capture later, to discover R2. So these guys are going to send out UDP multicast as soon as they have LDP enabled interfaces, similar to how OSPF would work. Where we start to deviate from something like how OSPF would discover its neighbors is as soon as these guys discover each other, so as soon as they pick up each other's hellos, they're going to immediately switch to a TCP unicast. So the UDP multicast mechanism is only meant for you to find out where your neighbors are and who your neighbors are. It's also meant to discover their capabilities, including their router ID. So the UDP multicast, within that hello message, it contains the transport address, which is the router ID we set. And then as soon as they switch to the TCP unicast, that's when we're using the local router's router ID as the source address and the remote router's router ID as the destination address. So we're not using UDP multicast to do the full neighbor formation. We're just using it to find where the neighbors are. And then as soon as we get that sorted out, then we immediately switch to using TCP to finish out the process, to send labels over, to finish forming the actual neighbor relationship using a unicast session instead of UDP. So it makes for an interesting, it makes for an interesting, what's it called, neighbor formation process, because it means that there's two ways that you can thwart LDP from forming a relationship. You can block the UDP process, and that means that they won't be able to discover each other, or you can block the TCP process, which means that they will find each other, they'll know that they exist, but the routers won't be able to go forward to actually form the relationship. And the reason you might want to cut off LDP from forming a relationship is for lab purposes. If you want to go ahead and try out features that involve failover and high availability and features like that. So that's that. So what we're going to go ahead and do from here is configure the rest of the lab. Any questions while I configure the IP addressing here?
Sure. Let me go through a couple. We have a question from Rick. I think when you were explaining the basics of MPLS, you said kind of like IP, like IP tunneling. It is similar that it's like a tunneling protocol, right? Like an IP.
Yeah, in a
it's not
sense,
tunneling exactly.
Right. Well, there's similarities. I wouldn't exactly call it a tunnel until you actually overlay the VPN.
Right.
But in terms of the encapsulation, there are similarities. I don't think I specifically said IP to IP, though.
Oh, that was Rick's question. Is it like IP to IP? There's similarities and there's differences. Yeah.
Right. For example, MPLS, the MP stands for multi-protocol for a reason. So IP to IP, you can only, or IP in IP rather, you can only encapsulate IP because you're using a specific IP protocol to encapsulate the IPv4 header within another IPv4 header. MPLS can encapsulate anything under the sun.
Right.
It's much like GRE in that sense. You can encapsulate IP, you can encapsulate IPv6, you can encapsulate frame relay ATM if you want. IPX, if you perfect the time travel machine, you go back to the 1990s when the frame relay circuits were being weaned out, you can run frame relay over MPLS. It's called Atom. It's the term is fairly weaned out now, but it used to be a thing that people did. So that's a thing you can do with MPLS. So unlike IP and IP, you're not restricted necessarily to what MPLS can encapsulate. MPLS, the header doesn't have a type in it. It's not like an ether type or an IP protocol. It doesn't really care what it's encapsulating, just that it is encapsulating something with a label.
Okay, cool.
Hope that makes sense.
Yeah. Oh, I just realized we got Orhan Ergin watching. Hi, Orhan. Good to see you.
Hi, Orhan.
There was another question earlier. Is there any role of Cisco Express Forwarding, CEF, in MPLS?
Yes. So I haven't mentioned it because honestly, if you don't have Ceph enabled, what are you doing? Ceph is technically required for MPLS to work. So if I were to go here and turn off Ceph for whatever reason, MPLS would fail to work. So you see some videos saying, okay, well, in order for you to proceed with MPLS, make sure you enable Ceph.
That's basically all you need to remember.
Yeah, it's like, well, who hasn't done that? These routers have that enabled by default, so I'm probably fine. That's why I didn't mention it. But yes, you technically need to have Ceph enabled.
Right. Yeah. Here we got another question. I can answer this one. Is frame relay still required in CCNA? No, it's not. It was taken out a couple versions ago. It was in the previous version of the CCNP.
Yes, I remember
routing
that.
and switching. Yeah, I had to study frame relay.
Same.
Good times. So that was switch exam, right? Yeah.
Routing exam.
That was right.
Yeah. Oh, and you can see here, this is confirmation of what I said earlier. So if you set the range after it's already allocated some labels, it'll use that range for new labels, but the configure range in the next reload for all labels is going to be this. It keeps the lower bound if you haven't reloaded the router after changing a range. Just wanted to point that out.
Nice. Okay. Yeah, so Ambrose, your question, frame relay, you don't have to know it for the CCNA anymore.
Any other questions?
There were a couple more. A second. Okay, another one. He said, as we know, MPLS uses Lfib. Is that correct? But our end device...
That's the forwarding structure. Actually, it changed it. So it's not real in the newer versions. It's not called an Lfib anymore. It's called the MFI, the MPLS forwarding infrastructure.
Okay.
You can keep calling it an Lfib. People will know what you mean. It's an internal change to these structures. It makes things a little more efficient there. So for all intents and purposes, yes, it uses an Lfib to do the forwarding. That's what the show MPLS forwarding table is showing you.
So he says, MPLS uses the Lfib, but the source and destination use a fib. How does the conversion from fib to Lfib take place? He asks.
Let me see if I can show you. So basically, I'll show you later. It'll work better when I have actual prefixes to work with there for customers. But basically, when you receive an IP packet, when the provider receives an IP packet, the label information will be encoded within the regular IP routing table and the regular IP fib. So when the PE receives the IP packet, does the routing for destination, it will see in the routing table, hey, this route has an MPLS label associated with it. Go ahead and when you do the encapsulation, throw on an MPLS label as well. So it's encoded within the IP route entry in the rib and the fib, in the regular rib and fib.
Cool.
Just have a couple more routers to configure here. So you can see here we have the Ldp coming up on the router 3. Router 4, this is the one where I'm going to leave a couple of these interfaces. Unconfigured because they lead out to customers. So I'm just configuring the certifier right now. It's part of breaking things down and not doing too much at once.
Yeah, just focusing on the core, right?
Yeah. So MPLS, gonna do the router ID first and the label range. Just so I don't have the routers try to provision labels before I change the range to avoid the whole restart issue. That's part of what I recommend doing for a lab before you label MPLS. Configure all your parameters first. And from there, that should work. Gonna configure R5 and R6, and we should be on our merry way. So, any other questions while I'm doing this?
Yeah, we just got a new one. Do you see service providers using VXLAN as an underlay within MPLS?
Haven't noticed it. So VXLAN is more of a data center underlay there, and there's a couple reasons why.
Right.
But no, I don't think so.
Okay.
Yeah.
Cool.
Oops. I can type today. Priority, loopback 0, MPLS label range. And we'll go into Ospf here, Mpls Ldp audit config, and then we'll enable Ospf here.
Cool. I got one more question
And
from earlier. How long is this
perfect, I got
class?
one more interface.
How long is this class? It'll be 2 or 3 hours. We'll see.
Yep.
I like to take our time during these live streams.
Yep. I'll try not to make the latter bits as boring as IP address configuration.
Yeah.
Mpls Ldp audit config, and then we'll enable Ospf here, and that's most of the core configured. I'll leave off R16 and R17 for when we need them. We won't need them just yet, but I'll do it when we do.
Okay, cool.
So we go ahead and show IP route. It seems I forgot to enable the loopbacks to work under Ospf, which would account for why I haven't got LDP forming yet. Yep. And by the way, just to make this note here, so if you notice, there's a little bit of discrepancy. So I said that MPLS would be enabled on any interface that is part of the IGP, which is kind of a lie because of this loopback here. So you notice that I have 4 interfaces under Ospf, I have 3 interfaces under LDP. And the reason becomes clear if I try to go under loopback 0 and force it to enable MPLS. MPLS is not stored on a loopback interface. And you might say, okay, well, you need a label for the loopback interface. We'll worry about that later. Not to worry, because we're forming labels for it. So MPLS won't enable, the LDP process won't enable on a loopback, but if your loopback is advertised within your IGP, because LDP is fundamentally just grabbing the label out of the routing table, you're fine, or rather the routes for which to label. So if you notice, we're labeling all of these prefixes here, and that's because they're in the routing table. So how LDP works and why we call it IGP plus LDP signaling is because LDP looks in the routing table of the router, and from there it grabs all the routes to be labeled and then sticks a label on them and advertises them that way. So for any route, you're advertising it twice. Once through IGP, that's the IP advertisement, and then another time through LDP, and that's the MPLS label signaling the advertisement for label. So it's just siphoning all the routes off the routing table and doing it that way. And that means that it also copies the next hop. So the consequence of this is that whenever you're using LDP, it follows the IGP path. So whatever the path that the packet would have followed in the context of IGP, so no MPLS, when you enable LDP, because it's just copying everything out of the routing table, including the next hop, including the outgoing interface, the MPLS path is going to be an exact copy. It's going to be a replica of the IP path. So you can get around that when you start using RSCP, but for the context of LDP, it's going to be a requirement. So if you want to engineer your MPLS path, you also have to engineer the IP path. So you have to do things like Ospf costs, things that you would have learned in your CCNP and your CCNA there, and then manipulating Ospf costs to force the IP path to go some other path. That's going to be the same process you have to use in order to influence the LDP path, because the LDP path is one for one the same as the IGP path. So that's that. So the way I verify here whether everything is working is, do I see all of the loopback interfaces for my routers? So I have routers 1 through 6 participating in MPLS. Do I see all of them here? And I do. Now, you can also test whether MPLS is working in the core. So by ping 6666 source loopback 0, this pings. Now, the question is this actually using MPLS in the transport, or is it just a regular IP ping? And the way you can tell is with Traceroute. So on Cisco routers, when you're using Traceroute will actually show you the MPLS labels.
Oh, cool.
And the way it does this is when the time expired comes back, the label is actually encapsulated within that. So there's an extension within the ICMP payload for the time expired that tells this receiving router what the label was at the point that the TTL expired. And so that's how you can get this hop by hop analysis of what the actual MPLS label is. And it's pretty useful for troubleshooting. Although I will say that if your MPLS labeled path is broken, this does no good for you. So if at any point, even if it's in the middle, if the MPLS path is broken in the middle, you will not see anything here. Your first hop will be all stars. And that's where MPLS ping and MPLS traceroute, the OAM components I mentioned earlier, come into play. What you can do with MPLS OAM, and that's enabled by default in iOS XE, is if you do traceroute MPLS IPv4, the target FEC, or the forwarding equivalence class address, which is, I was talking to Jeremy about this before the stream started, is the funniest word to make a pun with because it sounds like a particular profanity I'm not going to mention.
Don't say FEC too much. We'll get demonetized.
Yes. Get demonetized. But what you can do here is you can actually trace route source 1111 or 4444, I'm sorry, and verbose, and you can actually see what the path is here. This is going to show you where the break in the path is. It's going to show you a capital B for the unlabeled output interface, and that means that there's a break in MPLS. So whereas the IP tracer will be practically useless if your LSP breaks, and because you won't know where the break is, this MPLS trace route will show you specifically where the break is. There's also a version of ping that works with this, MPLS ping, and that's what you saw in the CCIE objectives. You can do something similar with that, and as is the case with regular ping, it'll show you that you're getting a response back from your destination, but not necessarily the hop by hop. So when you're troubleshooting MPLS, typically traceroute is going to be your go-to command for doing that. So what I'm going to do is I'm going to bring back the CML here because I want to go ahead and do a packet capture of a couple of things. I'm going to do it on this link here because it's going to allow us to see it all at the same time. So I'm going to go ahead and start the packet capture here. And within a couple of seconds, you should see that we have the UDP advertisement. So this is multicast to 224.0.0.2, which is the all routers multicast address for IPv4. And you can see here that we have the LDP payload, and in that payload, you can see that we have the IPv4 transport address. So this is an advertisement from R1, that's our source. So you can see the IPv4 transport address is going to be 1111. That's our router ID. You can also see that the LSR ID is going to be 1111. It's also our router ID there. Now, if I go ahead and drag this over here, I'm going to go ahead and retry our traceroute for MPLS, as well as our regular traceroute for IP. And we'll go ahead and see the type MPLS echo. I'll stop this, I don't need it anymore. You'll see a couple interesting things here. So this is the echo from our MPLS traceroute. The first thing you'll see here is the TTL. So this is the MPLS header. This is our label. So we have 4 fields here. We have the MPLS label itself, which is a numeric number. So in this case, 1007 was the label that was assigned by router 1, and that's why we set this label range. The second you're going to see is the MPLS experimental bits. Technically, if you want to go by semantics, this is now called the MPLS traffic class field. This is for QoS. That's the main use case for it now. You have the S bit, this bottom of label stack bit, and this is set to a 1 if it's the last label in the stack. So you can have multiple labels being affixed to a particular packet, and the processing routers need to know whether that particular label is at the bottom of the stack or not, whether it's directly touching what it's encapsulating, which is in this case IPv4 or not. And so it's a 1 if it is the last MPLS label, which in this case it is because it's the only MPLS label. And it's a 0 if there's another MPLS label that follows it. And you'll see that 0 when we start implementing LWVPN. The other thing that's really interesting here is this destination address. So you get told all your life that, hey, you don't forward traffic out to other destinations that have the loopback address in them, this 127.0.0.1 address, right? You don't, because that's the local loopback address. But the thing is that, and I'm showing you this in order to prove the point I made earlier, is that these routers here don't look at the IP destination. They just look at MPLS and they forward. And that's what's really important about this in the context of MPLS, because in the context of the MPLS trace route, you're using this in order to figure out whether there's a break in the MPLS path. You don't want the routers in the middle to pick up and do IP forwarding if there's a break in the MPLS path. If there's a break in the MPLS path, you want to know, and you want to go ahead and get that traffic returned so you can figure out where the break is.
Yeah.
That's what this does. So if in some event there's a break in the path here, and this traffic gets forwarded as a regular IP packet, when it hits that router, the destination is the loopback. It's not going to keep forwarding it. So that's the point of this destination.
Right.
That's just that. If this needs to be maintained all the way, this MPLS label needs to be maintained all the way, and if it's not, we want to know about it. And then we have it's encapsulated UDP, and then we have the echo here, the actual payload for the echo. We don't need to see much of that. If we go ahead and look at the ICMP, so I'll search for ICMP here, we can see that. Maybe look for something. Oh, whoops. We're not going to see MPLS label here. What we will see is the MPLS stack entry. So this is what I was talking about earlier. So how does this router know that the MPLS label here is 1007 at this particular hop? Because the time exceeded message from the ICMP that you get if you use Traceroute contains it as an extension, the MPLS stack entry extension. And it contains the MPLS label, the header exactly. And so it's going to tell you here what the MPLS label stack was at the point where it was stopped. And this works if there's multiple labels because it's going to look at the entire stack and send it back to you. It's useful for troubleshooting there. So that's that. When we look at when we actually get these customers set up here, we'll take a deeper look at how the actual label stack looks within the header. I'm going to drag this back over here now because we're going to go ahead and finish the implementation.
Cool.
So we have MPLS up in the core now. So as drawn out as that might have been, because I was going through and explaining each step in a fair amount of detail, this is actually not that much config. If we go ahead and do a show run, fundamentally all we did was we configured the label range. I'm going to look for LDP. We configured the label range, we configured the Ldp Router ID, and then we configured MPLS Ldp auto config. Everything after that was basic IP addressing, basic OSPF. That's it. And so MPLS is one of those things that's really easy to configure. And you saw that. It's 3 commands.
Yeah.
But it's a lot to take in. It's a lot to explain because that command on the back end does 10 different things. And so after we're done with those couple of commands, it's not all that many, we're done configuring the core. This core is now capable of supporting MPLS.
Wow.
But that's not worth much if we're not actually using MPLS to do anything. So before I move on to the actual fun part of this, where now we have our MPLS working, we're going to move on to doing the VPN stuff. Are there any questions about the core?
Not at the moment. If you guys have questions, feel free to write them in the chat. It's pretty cool how simple it is to configure. Like as complex as the concepts are, to actually implement it or do these basic configurations is quite simple.
Right.
I'm sure it gets more complicated, but
yeah, it's a lot. Yeah. So this is the most basic MPLS core configuration you can have. There's things that I might look at the end that help optimize this, but fundamentally, you've got an MPLS core now. No matter how simple or lacking in features it might be. So now we've got this core set up. If there's no other questions, I'll move on to the VPN side of this.
Yeah,
and
sure.
the VPN side of this, right?
Yeah, sure. Sounds good.
Oh, okay. I thought there was a question.
No.
So the VPN side of this is going to be where we start to throw together a bunch of advanced routing concepts. And MPLS is really a test of whether you understand routing or not. The core configuration is where a lot of your new concepts are. When you start moving on to overlaying an elder VPN over to MPLS, now you're getting into your routes, your basic routing there, your basic and more advanced routing. So part of the appeal to elder VPN is that you don't care what the customer prefixes are. So as I covered in the beginning, these service-side routers here, the only routers that need to care about what the customer prefixes are the edge routers, which means that if you're using a private range. The idea of a private range is that it doesn't matter how many people in the world are using the exact same private range because it's private, right? You're not advertising anywhere on the internet. But if you're pushing private ranges into a service provider environment, that might be problematic. A service provider has, potentially millions of customers, a lot of customers that might be using LWVPN. What are the chances that every single customer is not going to have an overlapping range? So,
Zero.
yeah, near zero, right? Exactly zero in the real world.
Yeah.
So the solution here is going to be a VRF, and that's the first thing that we're going to be configuring when we're touching on LWVPN. We're going to go on the provider edge routers, and we're going to configure a VRF. So for the hosts here, for the customer networks, there are 3 customers. We're going to be doing the first 2. The last one is going to be left for a feature at the end that I might cover. And the addressing scheme here is really simple. For both customers, if it's H1, then this third octet is 1. If it's H2, then this third octet is 2. And if it's H3, then this third octet is 3. The last octet has got to be 2 because the default gateways for them are 1. So if I do an IP route, the default gateway is default via 10.0.3.1. Same thing here. So it's IP route and IP route. So the last octet is 1. So it's the third octet we're mainly concerned about. But on customer 2, it's got to be the exact same story where H1 is 10.0.1, H2 is 10.0.2, and H3 is 10.0.3. And so we have overlapping prefixes. For both customers, host 1 is using the exact same IP address, host 2 is using the exact same IP address, and host 3 is using the exact same IP address. And we can get away with this because the LGVPN is going to separate each customer. If you're customer 1, let's say Samsung, and if you're customer 2, say Sony, you probably don't want their routes to mix with each other. Samsung probably has no reason to ping Sony, and the other way around. So the LGVPN with the use of VRFs are going to divide, they're going to create a big wall in the middle and separate everyone's routes. That way they don't leak into each other. That's what the extranet objective that I covered earlier was referring to. It's extranet punches a hole in the wall and allows certain routes to leak between customers, and you might have a use case for that in certain situations. But for the most part, that wall remains pretty rigid, even with your extranet. So that's that. So what we're going to go ahead and do, like I said, firstly, we're going to go on the PE routers, which are router 4, router 5, and router 6. And we're going to go ahead and configure VRFs. Now, VRFs can exist in 2 variations on Cisco platforms. You have VRF Lite and VRFs. The difference is that VRF Lite doesn't use MPLS and VRFs do. Well, we're doing MPLS, so now we're going to hop straight into VRFs. So for the VRF configuration, there's the old method and the new method. Old method being IPVRF, new method being VRF definition. We're going to have to create a VRF using the VRF name. And so we have 2 customers here, customer 1 and customer 2. Each customer gets their own VRFs. So we're going to go ahead and do VRF customer 1. We're just doing IPv4 there, so we don't need to do IPv6, although if you want to enable IPv6, you can. And there's a couple things we need to configure here, 2 to be exact. You have an RD and a route target. So RD stands for route distinguisher. And I saw a question in the chat earlier about what an RD and an RT is. Your route distinguisher is what allows for that overlapping subnets thing. So these routes are going to have to be advertised over BGP. BGP might get mixed up as to what VRFs particular routes belong to if 2 customers are advertising the exact same routes. That's what the route distinguisher exists to do. It's a BGP thing. Well, both of these are a BGP thing. So the route distinguisher is prepended to the actual network. So if your network is 10.100/24, the BGP advertisement is gonna look like RD, so 100:11 or whatever, and then another colon, and then the rest of the route. And so that makes it so that from a BGP perspective, even if the prefixes are the exact same, because they're in two different VRFs, they're going to have two different route distinguishers. They have to be unique. And because of that, BGP is going to see them as different routes, even though they're the exact same network. And that helps BGP from getting mixed up. So our route distinguisher, there's multiple ways you can format it. 4B ASN means 4 by ASN. So this is referring to 2 by ASNs. This is referring to 4 by ASNs. And then you can also do an IP address. But either way, it is something colon a number. I'm going to do the 2 by ASN. So the service area ASN is going to be 1000. And then this can be an arbitrary number. So this is customer 1, so we'll do 1. The other thing here is going to be your route target. So your route target is also a BGP thing. It's also included in the route, but in a slightly different way. So your route target is an extended community. And the point of the route target is that even if your route gets over to the other side, it needs to know what VRF it's going in. And that's what the route target tells it. The route target says, I am in this VRF. And the use case for that is, and the reason you don't just use a route distinguisher to do that is, let's say you have an extranet scenario. So I said I wasn't going to cover it too much, but it's a worthwhile example here. If you have an extranet example, one route is going to go into two different VRFs. You can't do that with a route distinguisher. It has to be unique. But you can do it with a route target. You can tell the VRF, I want you to import this particular value. And it's like a route tag, essentially. It's going to tag those particular routes and import or export whatever routes have that tag. So you need both import and export, because export tells the router what tag is going to be used for routes that are being advertised from this particular VRF. Import tells it what routes from remote routers, from remote PE routers, are going to go into my VRF. If you want to use the same route target for both, you can use both. Both is just a macro. It's going to issue two different commands, import and export. Works smarter, not harder. You can just do both if you're going to use the exact same route target for both, which we are in this lab. And it's pretty much the same format as an RD, which means that for lab purposes, you can just use the route target for both the RD and the RT, the exact same value, and it'll be fine. So that's that VRF configuration. Let's go ahead and configure this VRF here. We will use RD 1002, route target 1002. Not that much configuration, it goes into it. Now, I left these interfaces here unconfigured. And the reason for that is that if I had configured an IP address, so let's go ahead and configure an IP here. I don't really care what the IP is, it's going to get taken off anyway. So let's do that. And what's going to happen here, when I issue the VRF command, so let me make sure I'm doing this correct for the correct interface. If we go ahead and go to gig 2 and VRF forwarding customer 1, we can see that it strips off the IP address. And the reason for it is that it moves it to a separate routing table. So what a VRF does in order to achieve the address separation, the network separation, is that it creates new routing tables. So if I go ahead and do first I'll add an IP address to this interface here. So we'll do 10.4.7.4. If I go ahead and do a show IP route here, show IP route for 10.4.7.0, which is network, you can see I can subnet as in a table. If I specify this VRF customer 1 command, you can see that it is in the customer 1 routing table. So it creates separate routing tables for every single VRF and adds networks into there. And the routing tables don't talk to each other by default. So that way, it doesn't matter what's in one routing table from the perspective of the other. So we're going to go ahead and go back here to gig 3 and assign this to customer 2's VRF. And then we'll go ahead and IP address that. Now, that's that. We move on to the other routers now. What I'm going to do is I'm going to copy the VRF configuration. just copy this here. I'm gonna go ahead and copy that, add a config T so I don't piss my router off. I've just created Vrfs here, so what I'm gonna do is move on to my interfaces here. Vrf forwarding customer 1, IP address, it's gonna be 10.585. In G3, Vrf forwarding customer 2, IP address 10.5.9. What was 11 actually? 11.5. And then we'll go ahead and copy the Vrfs here as well. So if I go ahead and go right here in G2 should be IP or Vrf forwarding customer 1, IP address, it's gonna be 10.69.62.55.255.250, and we'll do the same thing for customer 2's Vrf, IP address 10.6.12.6. Should have that right. All right. So the verification you can do for this, there's a lot. Show Vrf. And that will show you the Vrfs there. You can do show Vrf detail. And that will show you a lot. It'll show you the import and export route targets. It will show you the interfaces that are part of it, and then I'll show you the default route distinguisher for it. So that's the configuration of the Vrfs there. Now we can go ahead and start configuring the BGP. So the advantage here is that you don't have to share customer routes within the core. But as I mentioned at the beginning of the stream, the PE routers still have to know the customer prefixes. The edge routers have to know the prefixes, the middle routers, the provider routers don't. Now, this is called a BGP-free core, and it's one of the big points of MPLS is that you can push the forwarding intelligence, what we call it, to the edge. And by doing that, we make it so that the core routers, router 1, router 2, router 3, are all just dumb routers. All they're looking at is the MPLS label, and they push it on, which means efficiency. You can have these routers here not care about the IP stuff. They just look at a label, follow instruction, and go and forward it, which relieves them of a lot of forwarding stress. It means that they don't have to maintain quite so much state in their control planes, which streamlines what these routers actually have to do in order to facilitate the forwarding there. But the provider edges still have to run BGP, so we're going to go ahead and do that. So router BGP 1000, and I'm going to go ahead and do no BGP deflow IPv4 unicast. So because we're exchanging the L3 VPN routes, we're not going to be using the IPv4 address family. We're going to be using the VPN v4 address family. And we're going to activate that VPN v4 unicast address family. And then we're going to go ahead and go under the neighbor statement here. So we have to configure R4 to advertise these routes to R5 and R6 because R5 and R6 both have customer 1 routers. Now, and customer 2 for that matter. Now, there's a couple ways you can do this. This is iBGP, realistically. So you're going to have to do it either using a full mesh or using a route reflector. There's also the option of using confederation, but not much point here. So we're going to go ahead and do using a route reflector. So we're going to make R5 a route reflector, and then we're going to peer R4 and R6 to it. So this is where your tested routing comes in. So we're going to make our MLAS here, 1000, neighbor 5555, update source loopback 0, and then we're going to activate the neighbor under our VPN v4 address family. That's all we have to do for now on R4. We'll move on to doing the rest later, but I just want to go ahead and get the VPN v4 stuff for it first. So we're going to go on router 5, do the same thing. We're going to activate BGP here. We're going to do no BGP default IPv4 unicast command, again, just so we don't automatically activate IPv4 since we don't need it in this demonstration. We're going to activate VPN v4 if I can type. And here we're going to make a peer group. So PE peer group. so PE standing for provider edges. And then we're going to go ahead and neighbor with router 4, remote AS 1000, 4444. We're going to call this update source. Whoops. Did not mean to do that. Neighbor PE, remote AS 1000, neighbor PE, update source, loopback 0, and then peer group PE. So that's going to cause it to inherit all the configuration of the peer group. Same thing for R6, and then the VPN before unicast. We can't do the PE activation here, because if we do that, it's not going to let us. So we have to activate each individual neighbor within the address family. But as soon as we do that, we can go ahead and configure our route reflector client here. Now we can go back to router BGP 1000, address family IPv4 unicast, or sorry, no BGP default IPv4 unicast, and then address family VPN v4 unicast, neighbor 5555, remote AS 1000, neighbor 5555, update source loopback 0, and then we'll go into our VPN v4 configuration and activate 5555 here. So we go ahead and view our BGP configuration. You can see here that we have the 5555 neighbor activated under VPN v4, and we also have the send community extended command automatically activated for us. This is going to go ahead and make sure that we can send our route targets, because the route targets exist as extended communities. And among other things that we're going to need to use there, route targets is going to definitely be one of the bigger ones there. So we need to be able to send the extended communities that we need, and that command is going to enable us to do so. It's a failover, or it's a fail-safe there in case you forget to enable send community extended. It'll enable it for you because you're going to need it. So how nice of Cisco to do that, right?
So considerate.
Yeah. So if we go ahead and look on router 5, which is forming neighbors for both of them, show BGP VPN before unicast, which is the way you're supposed to do it. In the older BGP commands, there's a way you can view VPN before there. But the new way to do it, the proper way to do it, I guess, is show BGP VPN before unicast all, and then this will show you the VPN before BGP table, which doesn't exist yet because we haven't advertised any routes. You can also do summary here, which is going to show you that we have our neighbor formations completed because we have our prefix received count here instead of some state. If you want more concrete verification, you can just do neighbors here, and you'll see the BGP state is established, and it's been up for 2 minutes and however long. So that's that. So now we have our BGP formed, and keep in mind, this is actually running over the MPLS. So the BGP open messages, all of that has been running using the label switching, and then the core has been forwarding MPLS this entire time in order to form the BGP sessions between the PE routers there. So now at this point, we can go ahead and move on to the customer routers. So R7 to R16, in this case, R7 to R9 for customer 1, and R10 to R12 for customer 2. So we go ahead and go to our customer routers. The first thing we're going to want to do is configure the interfaces with IP addresses. So 10.4.7.7. Keep in mind that this is just going to be simple configuration. Now we're on the enterprise side of things. So we've moved away from the service provider for a little bit. We're going to go on the customer side, configure the IP addresses there. Do the same thing for gig01, which leads out to our hosts. In this case, it's going to be 10.0.1.1. Just make sure we can go ahead and ping our hosts there. And we can. So let's go ahead and do that for the rest of our configurations. In this case, it's going to be 10.5.8.8. And then IP address 10.0.2.1. Ping, just make sure we can reach our host there. And then IP address 10.6.9.9. 01 IP address 10.0.3.1. So that's customer 1. Now, from customer 1's perspective, the LGVPN, all the MPLS that we just set up, is nearly invisible to him. And as a result of that, what we're going to have to do here is push the routing of service providers. So from the customer's perspective, the MPLS is invisible, and the service provider is this one big router, this black box that we send the route into, and it comes out on the other side at the other customer site. So we're going to have to advertise these routes to the provider. Now, in the real world, this becomes a negotiation matter between your service provider and the enterprise customer. So your service provider may offer a number of options for you to advertise your routes. Honestly, it's whatever you guys want. Any routing protocol is going to work. You can do Ospf, you can do ISIS, you can do EIGRP, you can do BGP, you can do whatever. Each routing protocol is going to have its own caveats. You can even do RIP if you want. And again, each routing protocol is going to have its own caveats. And this is where you get into the PEC routing conversation, where you're routing between the provider edge, which is R4, R5, and R6, and the customer edges, which are R7, R8, and R9, so the customer-facing routers. And we're going to have to advertise the Gig01 routes. Now, what we're going to do here is a couple of things. We can do BGP first. I'll show you the intricacies for that. And then I'll show you OSPF, because OSPF with MPLS VPNs makes for a really interesting conversation, because OSPF puts on a dress for MPLS. It dresses itself nicely. It puts on the spray tan, all of that. It goes out of its way to make your life hell for MPLS. So it's necessary, but it adds a lot of complexity when you introduce the VRFs in the conversation. So what we're going to do, firstly, is run BGP just so we can avoid that mess for a little bit until we can get the LGVPN up and running. And then I'll go ahead and overhaul this, run OSPF for one of these customers, and I'll show you why OSPF starts to become a little bit different when you start using it for an LGVPN. So what we're going to do is we're going to run BGP, and here it's going to be the customer AS number. Let's call it 2000. Let's call it 100, or let's call it, let's say private AS, right? 65001. Now here it's going to be an IPv4 peering with the provider. It's not going to be VPN v4, although the service provider side is going to pick it up as a VPN v4 relationship because from its perspective it's holding in a VRF. I'll show you that later. But from the customer perspective, it's real simple. We're going to create a neighborship here, 10.4.7.4, remote AS 1000 name, and then that's it. Because it's directly connected, so we don't have to do BGP multi-hop. And then we're going to go into our address IPv4 unicast there and advertise the network, 10.0.1.0, and then mask is 255.255.255.0. Just like with regular BGP, you have to make sure that this matches up exactly, and you can verify using realistically sharpie BGP. And you can see the routes right there on router 8. Let's go ahead and do pretty much the same thing. So router BGP 65001, BGP route, and then neighbor 10.5.8.5, remote AS 1000, address IPv4, network 10.0.2.0, mask is 255.255.255.0. Int, and then router BGP 65001, neighbor 10.6.9.6, remote AS 1000, address IPv4, network 10.0.3.0, mask. And we can see that this is being advertised over. Now, not much use is injected into BGP, but we don't have a functional BGP peering. Let's go ahead and get that working. So router BGP 1000. Now, what we're going to have to do here is start off by going into a new VRF. So because these routes are coming in a VRF, these peers exist in a VRF from the PE side, we're going to have to configure our routing protocols to be VRF aware. That way they can form their peerings and know that, okay, this peer's routes have to go in this particular VRF. And the way you do that is by configuring a VRF here. So address family IPv4 VRF, and then what was the name of the VRF we configured earlier? Customer 1. Now from here, we can go ahead and configure our neighbor. So 10477, that's the customer router, 65001. And in a moment, we should see, if we give it a moment here, that we have this come up. Now, from the customer's perspective, this is just a regular BGP relationship, the regular IPv4 BGP relationship. From the provider's perspective, it kind of squashes it all into VPN v4. So it's not technically a VPN v4 relationship, it's an IPv4 peering that exists inside of VRF. Therefore, iOS XE calls it a VPN v4 relationship on the provider side. It's a criticism I have, and on iOS XR, it's not nearly so confusing. But on iOS XE, they like to squash it into VPN v4. I don't like it either, but what can you do? And the other thing we're going to do here is we're going to go neighbor 10477, and then we're going to run a command called AS override. And the reason for this is we can see here that R7, if we do a show IP protocols, is running BGP and AS 65001. Let's go on any one of these other customer routers. They're also running BGP and 65001. Because realistically, if you're a single enterprise customer and you have a public AS at all, you probably don't have multiple public ASs for every single site you run.
Right.
So the problem with that is that the main BGP loop prevention mechanism is going to be to check the AS path, and this is basic BGP. If you have a loop going around in eBGP, the way that you kill that loop is if a route loops back around in eBGP, comes back into your AS, the receiving router checks the AS path to see, is my own AS in here? And if it is, then it drops it. The problem here is that this isn't a loop. It just so happens that all of these sites share the same AS. So if we advertise this route over to another customer router from R7, say to R8, through the service provider, well, R7 prepended the AS path with its own AS when it exited the customer site and entered the service provider. When it comes back around and enters the second customer site, the remote customer site, it's going to see its own AS in the AS path because they're all using the exact same AS. So the way we kind of get around that is we use AS override. And AS override on the service provider side is going to have the service provider override that AS to its own AS. And that way, when it comes back around and hits the customer, it's not going to have its own AS in there. The other way to do this, because this requires configuration on the provider side, if your provider hasn't done this, the option that you, the enterprise customer, can actually do is a little bit less optimal. The ideal way is to have the provider do the AS override. If you can't have that happen for whatever reason, if your provider is unwilling, you're going to have to go into the customer side here and override that prevention mechanism by doing an allow AS in. And this is what this is going to say is basically kill the loop prevention mechanism. If I see my own AS, I don't care. Now, of course, the reason that this is not optimal is because it means that there's no loop prevention anymore. But because you're likely just peering with this provider for your MPLS VPN, the chances of that happening, because these are all private routes, are basically none. So it's probably fine, trademarked. So from here, we can go ahead and configure the same thing on the rest of the routers here. Adjust IPv4 VRF customer 1. We'll configure our neighbor 10588 remote AS 65001. We'll configure the AS override to take effect, and we'll do the same thing on router 6. Whoops. Adjust IPv4 VRF customer 1. We'll configure our neighbor 699 remote AS 1000. Neighbor 10699 AS override. Whoops, did not mean to do that. 65001 and AS override. So, go ahead and take a look now. Let's do a show BGP VPN before unicast all. We can see we're now learning all the routes. And the important part, so we're learning these routes from the remote provider edges. The important part is going to be to verify whether we see them in the routing table for customer routers. And we do. So we're seeing these remote customer sites, so 10.0.2.0, which is H2, and 10.0.3.0, which is going to be H3. And just to cover my stones here, you can see that in the BGP, the BGP table output, this is where our AS override kicks in. So it overrides the 65,001 AS that's there with its own AS. So you can see there's two instances that go search by your AS, one that's legitimate from the export and one that was overridden from the customer AS to the provider AS. So if we go ahead and ping from one customer site to the other within customer one, we can see that hopefully this works, and it does. So we're pinging the IP address of host 2 here within customer 1, and it's working. I can also try pinging the host address for customer 3, or for site 3, and we can see that's also working. I can go on host 2 and try this as well, so 10.0.1.2, and you can see it's working from there as well. So that's LDVPN. We've just configured LDVPN. And if we want to go ahead and verify that this is working, we can go ahead and do a packet capture. So I'm going to go ahead and leave this ping going. And we're going to bring this back over here because I want to do a packet capture. We're going to packet capture off of okay, apparently we're packet capturing off of nothing. Click. Let's reload this.
Oh, there we go.
Okay, now let's click. We're going to start this. We're going to go back to our pings. And 4 should be enough. So ICMP. And we can see here that we have our MPLS headers. So this is now working a data plane. And we're using MPLS to get over now. So we can see that we have our top label here and we have our bottom label here. The top label, as you can tell because I set the label range, is being generated by R3, which makes sense because we're sending it from R2 over to R3. And so it makes sense that we're using R3's label. And we're also using this bottom label here. So we have two labels in the label stack. This top one is going to be called our transport label. The bottom one is called our service label. So this is what we're generating via LDP. This service label is why we have LDP, or is why we have VPN v4. So if we go ahead and go back to our provider, firstly, if I do a show IP route for 10.0 or VRF customer 1 10.0.2.0, you can see here that, and this is in response to that last guy's question about, well, how do we know that the IP packet needs to be encapsulated using MPLS? This is how. So we have our MPLS label, which is 5011, and it's going to say MPLS is required. And we're sending it out of an MPLS-enabled interface. And you'll see a similar story if you look in Ceph, and we say 10.0.2.0/24. You can see that we have our next hop, our IP next hop, as well as that we have an MPLS label here that we're throwing on it as well. And this 5011, well, first of all, we need to figure out how we're getting these labels. So first of all, 1006, let's look at that in our Lfib. So this is our Lfib show MPLS forwarding table. We're going to look for 1006 here, and you can see 1006. So our local label is 4009, but the label that we're going to use to send the traffic is 1006, and this is the label that we learned using LDP from R1. So we do a show MPLS LDP neighbor. We are neighbored to R1, and so we're learning R1's labels, and that's this 1006 label. And you can see the prefix here is router 5. So again, we're not sharing any of the customer routes. In fact, if I go to a router in the core and I try to look for the customer routes, none of them are there because they're all in VRFs. So these core routers are in the global table, but all of the customer routes are in the VRFs. And so these core routers, because they're not participating in BGP, learn none of those routes. The label that we're using gets it to router 5. That's the top label, the transport label, what these routers actually use to transport. And in the VPN label, we learn via BGP. So if I go ahead and run this command, show BGP VPN before unicast all labels, this is going to show us that for this 1002 prefix, which is what I looked up earlier, we have the next hop of 5555, which is what gets it resolved to the top label of 1006. And then the bottom label is 5011. This bottom label, this VPN label, is basically used to tell the remote PE what particular VPN prefix and what particular VRF this goes in. So when the remote PE receives it, it receives it in the global VRF, but obviously our customer is not in the global VRF. It receives it on its interface to R4, which is within the service provider, it's within the global table, but it needs to route it back to a VRF for the customer. And so this is the label that helps it do that. It pops the label that gets to R5. At the very top, it's going to be this 5011 label. And so when R5 goes to route the traffic back down to customer 1, it's going to use 5011 in order to identify what the actual VPN prefix is, what the customer network specifically is, and then what VRF to route it down to. So that's that, and that's our L3 VPN. Now we can go ahead and replicate this, and with MPLS practice, we can go ahead and replicate this for customer 2. So if we go ahead and do a sharp interface brief, I don't think I didn't IP address this, but that's okay. 41010. So now we know how MPLS, or how this works. It's fairly simple to configure. 10011. So again, we have overlapping prefixes here for our customers. IP address 10.5.11.11 and G01 IP address 10.0.2.1. We go to 12 here, IP address 10.6.12.12, IP address 10.0.3.1. From here, we can go ahead and ping, or not ping rather, configure our BGP. So BGP is 65,002. Neighbor 10.4.10.4. And then address SAMI IPv4, we're going to advertise our network. We're going to go ahead and do the same thing over here. And then we're going to do the exact same thing over here. Neighbor 10.6.12.6, remote AS 1000, and then address IPv4, we're going to advertise this network over. That's it for the customer configuration. And on the service provider, all we really have to do is repeat the steps that we did earlier, except this time in the customer 2 VRF. So 10.4.10.10 remote AS 65,002, neighbor 10.4.10.10 AS override. Router BGPs 1000, IPv4 VRF customer 2. We're gonna go 10.5.11.11 remote AS 65,002, 10.5.11.11, and then AS override. And then 65,000 or 1,000 rather, VRF customer 2, 10.6.12.6 or 12 rather. And we'll do the AS override here too. So that's up. So we go ahead and do a show BGP VPN before unicast all. You can see that we've learned routes for both customers this time. So we have the VRF for customer 1, we have the VRF for customer 2, and you can see that we have the overlapping networks here. Now, if we go ahead and go back to router 10, show IP route BGP, you can see that we are learning, so this is customer 2 this time, we're learning the BGP routes here for our remote sites. And if we go to customer 2's host devices here, and we do the exact same pings that we did on customer 1's side, you can see that now they're working. And just to prove that this is entirely separate, that there's no route leaking between the customers, what I'm going to do is for one of these customers, I'm going to change the last octet here, etc net plan sudo vi 51 network.yaml, and I'm going to change the last octet here to 3. And I'm going to sudo net plan apply. So for customer 2, host 3 is now 10.0.3.3. For customer 1, it's still the same 10.0.3.2. If I'm on customer 1, I can ping 10.0.3.2, but I can't ping 10.0.3.3. And if I'm on customer 2, you can probably predict that it'll be reversed. I can't ping anymore 10.0.3.2 because this was going to our host 3 and our customer 2 in the environment, but I can ping 10.0.3.3. So it's proof in the data plane that this isn't being entirely separated, that the routes are not being leaked at all, that this is all remaining within the various customer sites, which is a good thing. So if we go ahead and go back over here to our PE routers, a couple more things to investigate before we call the LGVPN configuration with BGP SDPEC routing protocol wrap. The first we're going to go ahead and take a look at is show BGP VPN before you cast all, and we're going to go ahead and take a look at these routes. So what I'm going to do is Vrf customer 1, and we're going to take a look at the route for customer 1. So this is the 10.0.10/24 route. This is what I was talking about with the route distinguisher. So the idea of the route distinguisher, I'll pull up customer 2's routes for comparison. You can see here that customer 1's routes have this 1000:1 route distinguisher prepended to them because that's what we configured in the VRF. And same thing for VRF2, except with its respective route distinguisher. And again, this is just to make sure that within BGP that the routes don't get mixed up and that you're clear on what VRF each route belongs to it and was originated from. Then you move down here and you see that we have an extended community. This is our RT, or our route target. We have the MPLS label as being advertised here. And so this is MPLS label in. We are not advertising a label because this is the route we're locally learning. If we go ahead and change here, you can see that we would have an out label. But these are routes that we're learning from our customers, so we aren't. What this no label means is that when we send traffic down to the customer, we're not using MPLS labels. This is just regular IP traffic. And that's that. So that's the VPN before configuration. That's an Ultra VPN working.
Cool.
So as I demonstrated when I did the customer 2 configuration, if you get this practice down, it's not that many commands. And as long as you understand what you're doing, it's not going to take you that long to lab if you want to lab it up. Now, there's a ton you can do with MPLS, and that might take you a while, and it'll probably take you a while when you're starting to learn it. I remember my first LDVPN lab probably took me upwards of 2 to 3 hours to complete just because I was constantly trying to reference what commands to use. But after you get the hang of it, after you understand what you're doing, it's pretty quick.
Yeah, it seems like not all that complicated. I'm sure for people just working on their CCNA, this can seem a little complicated, hard to understand. But once you get to the CCNP level, like all these commands are very familiar, and yeah, it seems quite understandable and easy to set up.
Yeah.
Cool.
Yep. Are there any questions as far as the LGVPN site goes?
Nothing at the moment.
If not,
more of a comment. Your topology looks like a transformer. Interesting. Let's see that topology again.
It looked like a robot. Yeah, I was gonna add eyes to it. I was gonna add like 2 switches here or something, make eyes out of it.
Yeah.
We can do that right now, actually.
Yeah, why not?
Yeah, we'll make
switches.
2 little ugly eyes for it.
There we go.
Yeah, there we go.
Transformer complete.
Yep. So what we're gonna do, a couple last things here. as I suspected, the Ldp VPN explanation took a little while. We don't have a lot of time for some extra flair, but I did promise we would show you OSPF, and I'm not going to break that promise.
Yeah, sure. Let's do a little bit more.
Yep. So what we're going to do is we're going to remove BGP from this side. I'm not going to touch the service provider side because I don't really care. We can leave the service provider BGP configuration intact, and I'm fine with that. Because with this side down, it's not going to form a neighborship anyway, so it's harmless. So we just remove BGP from all of customer 1's customer routers. If I go ahead and try pinging now, whoops, 2.2, we have a destination host and reachable. We don't have routes. We check on customer 2. Obviously, it's going to keep working because customer 2 is still up. So these customers are completely independent from each other. Even if I bring down customer 1, customer 2 will keep on rolling. Now, what we can come back to is on R7, I'm going to configure OSPF. And here, what we're going to do is we're going to configure, that's it. I'm fine with that. And then we're going to go ahead and go on int G00 will enable IPOSPF 1 area 0. That's that. So int router OSPF 1 int G00 IPOSPF 1 area 0. And then I'm not configuring a global process, so I'm fine just configuring it this way and letting it initialize the process. So that's that. So what we can do here on R4 is we're going to have to configure OSPF. Now, we can't use OSPF ID process or process ID 1 because we're already using that for the core IGP session. And the way that OSPF separates the VRFs is by different process ID. So we're going to go with 101. VRF customer 1, and that's how we do that. And then we're going to have to go to G2, IPOSPF 101 area 0. Now, here's something else that you've been told probably since your CCNA. So when you start learning OSPF, you learn that the process ID doesn't really matter, right? It's just a locally significant number that's used to identify the process.
Right.
When you start, here's one of the differences. When you start using OSPF with an LGVPN, it does matter. It's no longer locally significant. And I will show you why in a moment. But here we're definitely going to want to match up OSPF 101 here. So I configured 101 over here. So we're going to do 101 over here as well. And I'll show you why it becomes globally significant in a moment. What we're going to do is go here on our customer interface, do that. And then router OSPF 101 VRF customer 1, IPOSPF 101 area 0. So in theory, yep, we have our neighbors coming up. And as well, I need to go ahead and advertise the networks all over here. Now, to be clear, it doesn't really matter what your customers are using for their process IDs. So the customer process ID isn't the one that's relevant. It's the provider process ID that's relevant. I probably misspoke there. So IPOSPF 1 area 0. So my customers could be using 101, 102. Doesn't really matter for them. It matters for the provider because it's relevant when you start doing the redistribution. So if we go ahead and look at our provider edges now in the customer routing table, so this is the VRF routing table, you can see we're learning the OSPF route here. Now, we have OSPF running between the provider edge and the customer edge. So the lingo is that OSPF is our PE to CE routing protocol. And we're using BGP VPN v4 between the provider edges. So it's the same old question as you've been dealing with in your multi-protocol routing labs. How do you take routes that are in one protocol and move them into another? You use redistribution. So you want to take your OSPF routes and inject them into BGP. So you can go into BGP here, adjust family IPv4 VRF 6, customer 1. And then here you can do your redistribution. Redistribute OSPF 101, and that's it. That's really all you have to do there. Now, the alternative is you can do network segments. Not particularly viable because that means that for every single customer route in every single VRF, you would need to have separate network segments. That's why you do redistribution. But you can if you want. So if you go ahead and do a show BGP VPN v4 unicast all, in the customer 1 VRF, you can see that we have this route that's being advertised here. You're also advertising this segment route for the physical segment going to the customer. You can do route map filtering if you want to go ahead and filter it down to just being the customer routes. There, you can say like match on a route source, but we're not gonna do that here just for simplicity. You can go back here, router BGP 1000, address IPv4 VRF customer 1. We'll do a neighbor statement, redistribution command. Show BGP VPN v4 unicast all. You can see that now we're redistributing 10.0.20 from OSPF into BGP, and you can tell that it's redistribution because the origin code here is a question mark. That means incomplete. That typically points to redistribution or an incomplete or an unknown source protocol. Same thing on router 6. VRF customer 1, we're going to do redistribution for OSPF 101. So we go back to router 4 here. You can see now we're learning all of this stuff. Mainly the stuff we're concerned about is 10.0.10, 10.0.20, and 10.0.30. Again, all of these guys are going to be the physical segment addresses that just got redistributed because they were included in OSPF and they were in that VRF routing table. So if we go back here to Sharpie route, oh, that's right. I need to go back and redistribute these. So this is mutual redistribution. So you need to redistribute from OSPF into BGP, but you also need to redistribute on the way back from BGP into OSPF. So we need to go into our OSPF process, redistribute BGP 1000. Now, if you're familiar with BGP redistribution, these are iBGP learned routes. If you're familiar with iBGP, you'll know that there's a command in BGP that you need to run typically when you're doing redistribution for internal routes, and that's this BGP redistribute internal. That's what I'm looking for. So there's the redistribute internal command, and it's marked as dangerous because it's from a design perspective, redistributing BGP into your IGPs can be dangerous from a loop prevention perspective, from a design perspective. So that's why that command is there. By default, you can't redistribute iBGP routes into IGP unless you accept the terms and conditions in a sense. Like, yes, I realize this is probably dangerous. I know what I'm doing, though. I need to do it. But in the case of a redistribution for Mpls VPN, where you have the address handling and a VRF, you don't need to do redistribute internal. It'll just redistribute. So if you go back here to, well, first you have to run the commands here, redistribute BGP 1000, and then redistribute BGP 1000. If I do show run as OSPF, you can see here that the redistribute BGP 1000 command is now in my OSPF 101 configuration. If I go ahead and do a Sharpie route, so you can see here we have OSPF routes. And if I go back to my customers, you can see here that now we're able to ping. So whereas above, when we took out our BGP for our BC routing, we got destination host unreachable. Now we're able to reach our hosts, and we can do the same thing for 3.2. And this is still separate. So if I do 3.3, as is the case for customer 2's host 3, we can't reach it. Now, I mentioned earlier that OSPF has some big differences when it's running in a LWVPN. Notice this. So for reference, when I went on the PEs, the way I did this was I did a redistribution command. Redistribution should have made into an external route. This is an inter-area route.
Interesting.
And here's why. and this is where our process ID starts to come in handy. So show BGP VPN before unicast all. Actually, no, Vrf customer 1, 10.0.1.20. So above, we just had our route target. When we were using BGP all the way around, we just had our route target. Now we have a couple of other things. So Ospf Router ID, I'm going to work backwards here because this is the big one. The Ospf Router ID, this is an extended community that tells you what particular router we distributed this. So what was the originating router for this? We can see that was router 5. The Ospf route type, so this is the case, another case of acronyms overlapping. So you have route target and route type.
Right.
The number that's relevant here, there's a lot of gibberish, but the number that's relevant here is 2. So you can look it up online. I don't remember the exact route number associations for the route types. But basically 1 or 2 is going to mean that this originated into the topology as an intra-area route. If it were redistributed, let's say, this route type number would be different. I don't remember what the number signifying that was an external route to start off as is, but there's a number for it. So it's administrative. It signifies what the original route type was when the customer edge advertised to the provider edge. Finally, you've got the list. This is your Ospf domain ID, and this is why when you redistributed the BGP route, the BGP routes into Ospf, that they showed up on the customer as inter-area routes. If your domain ID is the same on both ends, then the redistribution comes across as a inter-area. If they're not the same, then it comes across as an external route. Because if you think about it, right, the only reason we're doing redistribution is because we're having a transit a service provider, but fundamentally this is all one routing domain. These are all one customer routes, right?
Right.
So this is all one customer that's advertising all these routes. Doesn't really make sense to say that they're external to the AS. So therefore you inject them as inter-area. That way you still have preference over your intra-area route. So let's say you have some routes that are being learned between customer routers that are not via your Mpls VPN. You might want to prefer those routes over your Mpls VPN, but you might want to prefer your Mpls VPN routes over, say, routes that are truly external, that have truly been redistributed. And that's the point of injecting as an inter-area route. And the reason that the Ospf process ID comes into play is that if you actually decode this here, if you decode this number here, this is the representation for Ospf process ID 101. So by default on iOS XE, the domain ID is the process ID. So it encodes 101 into the domain ID for this particular route. If I change this to 102, let's say this would be entirely different. I mean, heck, let's do it. So I'm going to go on router 5 here. I'm going to show why I'm going to prove that the process ID is now globally significant. So I'm going to remove 101. I'm going to change this to 102, redistribute BGP 1000, and then I'm going to go in G2 IP Ospf 102 area 0. This should form. And if I go back here, what you should see after a little bit, in theory, let's look at show run as Ospf. Whoops, wrong router. Oh, whoops, I forgot. I have to redistribute back into BGP because I changed the process ID. All right, this should work now. There we go. So you can see that we have some routes that are OE2 and some routes are OI8. You notice that the routes that come from router 8, that's Ospf neighbored with R5, the one that doesn't have the process ID consistent with the others, are showing up as external. If I go to router 8, this is going to be most pronounced. You can see here that everything that's showing up on router 8 is now external. And the reason for this is that when R5 redistributes the BGP routes back into OSPF, because this is an LGVPN, it checks the domain ID and it calculates its own domain ID and it doesn't match. It does a comparison. If they don't match, then it redistributes as external. If it does match, it redistributes as type 3 as inter-area. So that's that. That's why now that you're doing OSPF with an LGVPN, that this process ID is no longer locally significant, it's globally significant. The other thing that I'm going to go ahead and show here is if you go ahead and do a show IP OSPF 101 rather, sorry. You can see here that we are connected to the Mpls VPN super backbone. And as well as that, any OSPF process that you stick in a VRF, if you don't do the capability VRF light command, which tells OSPF that, no, I don't have MPLS running, this is just a VRF light, no MPLS, just a regular VRF, it's going to automatically mark it as an area border router, even if it's just running single area. So this is just area 0. I haven't configured any other areas, but it's still registering as an area border router. And the reason for that is a design thing. So there's actually a cool guide I'm going to pull up here from Peter Lapukov, and I'm pulling it up only because I'm too lazy to actually draw out the topology, and he's done it for me, so might as well use this. But this is it. So I'm going to drag this back over here. So this is a really good guide as to how OSPF handles loop prevention. It's by Peter Lapukov, a legendary guy. You can find it on INE's website there. And if you scroll down here, he talks about how MPLS does loop prevention. And this, and let me see if there's a better topology. Yep, there it is. So basically, when you learn OSPF, you learn that area 0 is the king of all areas. It's the backbone area, right? It's the thing that handles the inter-area type 3 LSA traversal, right?
Right. Yeah.
Well, when you're doing redistribution with LGVPN, now you're adding a super backbone. So this is now going to supersede area 0. Area 0 is no longer the king. It's the king within that particular AS. But since you're doing redistribution into BGP and you're going through BGP, you're going through VP and V4, and then you're redistributing back into OSPF on the other side, OSPF treats the BGP redistribution, this abstract concept, as the super backbone, as the thing that connects the disconnected OSPF domains. Because right now, each PE is running its own OSPF domain with the CEs. So R4 is running OSPF with R7, R5 is running OSPF with R8, and R6 is running OSPF with R9. Now you've added BGP into the mix, now you're connecting the area zeros, and you're doing so using a higher area that's the super backbone. And so R4, when it does the redistribution, it makes itself part of the OSPF super backbone. So it's not lying. It is an area border router. It's an area border router because it's part of area 0 and it's part of the super backbone. It's part of 2 areas. And the requirement for being an APR is that you're part of area 0 and you're part of another area. In this case, you're part of area 0 and you're part of the super backbone.
Is that the standard name for the area, super backbone?
Yes.
Okay, interesting.
So there's no, because it's not an actual area, right? It's just an abstract concept. It's the OSPF concept for the OSPF to BGP redistribution.
Okay.
And this backbone is what bridges the otherwise disparate, otherwise disconnected area zeros that exist between each PE there. So it's a loop prevention thing, and the reason that this is relevant, and Peter probably could do a much better explanation of it than I can in his paper. The reason that this matters is because ABRs have some special characteristics. They can generate type 3 LSAs, which is what allows this to redistribute into a type 3 LSA. So ABRs can generate type 3 LSAs, and they also don't accept type 3 LSAs outside of their own area, or outside of area 0, which means that if this is truly an ABR, if it actually is connected to area 1, and for whatever reason it's receiving a type 3 LSA through area 1, it's going to drop it, which makes for some really interesting problems. If you're not using MPLS here, if you're doing multi-area OSPF and you're for some reason receiving type 3 LSAs to a non-backbone, non-area 0 area, it creates some interesting problems because as an ABR, it is obligated to drop those type 3 LSAs that are not being received via area 0. He talks about some more here. He also talks about a thing called sham links. And sham links are relevant because if you have a intra-area route, so the best you can redistribute is an intra-area route, as we saw, right? So if your process IDs match up, if your domain IDs match up, it's going to redistribute as an intra-area route. If you have a backdoor link, and a backdoor link is like a backup link, right? Let's say you have like a T1 circuit running between the customer sites, and you're running OSPF over that T1 link, and they're in the same area, it's going to be a type 1 LSA. It's going to advertise it as an intra-area route. And the effect of that is that if you're advertising customer routes over that T1 link, maybe you just want to use that T1 link in case the service provider goes down and the Mpls VPN goes down. But the effect is that the T1 link is now your preferred link. Not because of metric, it doesn't matter what the metric is, because metric comes in last in comparison to the route type. So because it's an inter-area route, it's always going to be preferred over your inter-area MPLS VPN redistribution, no matter what it is, no matter what the metric is.
Right.
So if you're in that scenario, if you're in that kind of hole where you need to have the MPLS VPN provider supported, in a sense, rather preferred, that's what I'm looking for, then you have to call your provider. This is the provider configuration, and get them to configure a sham link. A sham link, if I go into Router OSPF 101 here, area 0, you can configure a sham link. And the sham link goes between the PEs, and it's basically a tunnel. It's an OSPF tunnel that allows these PEs to communicate via intra-area routes. So now you're not advertising the type 3s to your customers, you're advertising type 1s to your customers. And that makes it easier for them to have the MPLS VPN preferred, because if it's the same route type, if it's all type 1 LSAs, then you can use metrics in order to manipulate the routes. It's not too common, mainly because if you've ever called your ISP, you know they're not the hardest working people in the world. So getting them to do sham links doesn't happen. It's not unheard of. I've heard some stories of sham links, but it's not ubiquitous, let's say that much. So you have to figure out some other options if your provider is not willing to do sham links, because this is all provider configuration, nothing to do with the customer besides how the routes come out. All the configuration for sham links happens on the BEs, which means you have to get your service provider up their butt and see previous note about them not being the hardest workers. So you have, if they're not willing to do it, you have to figure out some other solution. Maybe instead of OSPF over your T1, you run EIGRP over your T1 and leverage the fact that EIGRP has a lower administrative distance in order to get it preferred. That's one way you can do it. Or if your service provider offers you a choice, you can say run eBGP, because eBGP has an AD of 20. That would be preferred over OSPF, which would be running over your T1. So you have to be creative if your provider isn't willing to do sham links for you. So that's that. So I was going to cover L2 VPNs as kind of a wrap up, but I figured this is probably enough for a night.
I think we've covered quite a bit.
Yeah. So for the enterprise track, you're mainly going to be concerned about your L3 VPN functionality. If you are looking at a service provider track, or if you're interested, you look at MPLS and say, wow, this technology is so cool, I want to run some other stuff over MPLS because it's just a transport. L3 VPN is one type of service you can run over it. There's plenty of others you could, like L2 VPN, which instead of turning the service provider into a big black box router, turns the service provider into a big black box switch. So the difference between L3 VPN, and this is relevant for CCNAers too, the difference between an L3 VPN and an L2 VPN is that with an L3 VPN, the service provider is involved in your routing. So you saw here what the configuration was that we sent the routes into the service provider, and the service provider did all the BGP. The service provider handled routing the traffic out of the other end. With L2 VPN, it's all layer 2. So the service provider is not involved in your routing at all. That means that you can run OSPF directly between your sites and tunnel it over your L2 VPN.
Which implementation is more common, would you say?
L2 VPN.
L3 VPN, okay.
L2 VPN, the problem is that things like VXLAN, layer 2 gateways, those are L2 VPNs technically. But L2 gives you a lot less control, right? So the thing about L2 VPN is that it stretches the layer 2 domain across the service provider. So now you're running layer 2, a single layer 2 domain between your geographic sites, which if you can reduce your L2 domain size, generally it's the best idea. So that's why most implementations are going to use L2 VPN. The thing you would use L2 VPN for is things like data center interconnects, where you're interconnecting data centers. That's one of the things you would use L2 VPN for.
Okay, cool.
So that's that. That's as much as I have today. I could cover more, but it's 9:18 for me.
Yeah, I think that was quite a good introduction to MPLS, and then beyond introduction, covered definitely what you need to know for the CCNP NRC, and I'm sure some of the CCIE implementation also.
If you want more, there's a book that I really like.
Yep, I got this book. Just started it.
MPLS Fundamentals. He also has a video series on O'Reilly if you want to watch that too.
Cool.
But Luke DeGuine does a really good job covering MPLS here. If you search MPLS for books, there's a ton of things there. There's the MPLS in the SDN era, which is also a really good book. There's MPLS Enable Applications, which is a really good book.
MPLS Sound.
Wouldn't really recommend this one. I don't know what this is.
I'm guessing it's not networking.
Yeah, I'm gonna guess that too. There's things like segment routing, so that's what I talked about with Spring. Clarence Phils, I don't know if I'm pronouncing his last name correctly, writes basically the only segment routing book on the market that I've seen that's good. So there's that if you want to learn more. Traffic engineering, you can get into MPLS QoS. I think there's a book on that. Yeah, there's an MPLS QoS book here. So if you do searching, if you do your homework and search, you can find some good books on MPLS. It's quite an abstract topic, as you've probably seen today. So book writers just snatch it up because it means that they can take something like traffic engineering and blow up into a 600-page textbook.
Right. Cool. Awesome. So I'm
gonna go ahead and cut out the screen share.
Yeah, sure. I'll go back to the cameras.
Yeah.
All right. So I had one last question. Well, Ambrose asks, so generally, what is your best description of MPLS? So can you give a brief summary? What did you just show us?
Too long didn't watch summary?
Yeah, TLDR.
Well, I would describe MPLS as a transport mechanism, and that's fundamentally what it is. So we touched on L3 VPN for a lot of the stream, but L3 VPN is just a service that we're most likely going to be running over MPLS. MPLS is just the underlying transport mechanism that uses label switching as the forwarding paradigm instead of traditional IP packet forwarding.
Okay. Yep. Sounds good. That's a good summary, I think. All right. So thanks, everyone, for watching.
Yep.
Thanks, Kelvin, for your time. Looking forward to the next one. Any ideas what we'll get into next time?
Multicast, maybe?
Multicast, cool. Yeah. We'll talk about that later.
Yeah.
Okay, thanks, guys. So this was MPLS, multi-protocol label switching. It's something you kind of have to know a little bit for the CCNA, but then definitely CCNP, CCI level. This is something you have to learn, you have to get into. So I think this was a very valuable stream for all of you, and for me too. Okay, thanks, Kelvin. I'll end the stream here.
Thank you.
See you guys next time. Bye-bye.
Thanks, all.
Bye.